Okay, so we were discussing the chapter on the frequency response of control systems. And in this chapter, of course, our input signal is a sinusoidal signal. And we can change the frequency of that sinusoidal signal to see how the system is behaving. That is, over which frequencies the system is acting as a system or a filter that will let the input pass through it, and over which frequencies it is going to stop the input at the output, or at least significantly deteriorate the input to the output. So we looked at two different methods of plotting frequency response. The first method was that you have a real part and imaginary part of a transfer function, and you can go ahead and plot the real part against the imaginary part, or you can plot the magnitude of the transfer function, which is a complex number, magnitude of the transfer function versus its phase as your frequency is changing, that is. And those plots are called the polar plot. And the second method, which is very frequently used in describing the frequency characteristics of any system, electrical, mechanical, or any other system, is the plot of the magnitude of the transfer function versus frequency, and phase of the transfer function versus frequency. As the frequency is changing, how the magnitude is changing and how the phase is changing. The frequency can be expressed either in angular form, radian per second, omega, or in cyclic form, which is hertz. So we did an example in which we had a low-pass filter, and for this example, we plotted the response in polar form, that is the real part versus imaginary part of the transfer function. We also looked at an example for the same circuit, low-pass filter, such that we plotted its response, magnitude response versus frequency, magnitude of the transfer function versus frequency, and phase of the transfer function versus frequency. Although on this slide, you see the magnitude versus frequency in linear frequency terms, and the magnitude versus frequency when the frequency is expressed in logarithmic form, that is using the semi-log x function in MATLAB. Semi-log x function works very well. We discussed that this morning as well in digital system processing class. Semi-log x divides the interval into equal parts, and it is easier to see the change in the response, even if the response changes only towards the lower frequencies, and you're going up to very high frequency, but still you will be able to see the response properly. But if the response changes towards the lower frequency, you're going up to very high frequency, and you're not using semi-log x like in this plot, the first one, then of course it is rather hard to see the change, especially if you're going to very, very high frequency. Then the low frequencies are just going to be squished towards your vertical axis. So it's always good and wise to plot the frequency response versus the semi-log scale x. Then we jumped on to Bode plots. So these are exact plots, as you can see, that you can plot using MATLAB or using any other resource. Bode plots are approximate plots. They are not exact plots. But the good thing about Bode plots are that the approximation is pretty straightforward, and it is pretty easy to realize how the response of a system looks like if you're plotting the Bode plot. That approximation is quite close to the exact plot, except you're missing some curves and stuff. But apart from that, the Bode plot approximation is quite realistic. So in Bode plot, we discussed that it's a logarithmic plot of magnitude, and we plot it versus the logarithmic scale on the x-axis. So to calculate the logarithmic plot, whatever your magnitude response is, I should put this as magnitude response actually. So this should be magnitude response. Whatever your magnitude response is, you take the log to the base 10 and then of course multiply that by 20. And the phase Bode plot, which we are going to discuss today, is simply the Bode plot of the phase of Gj omega, which is calculated as the arctan of the imaginary part of Gj omega over the real part of Gj omega. Bode plot we discussed for different cases. If you have a constant value, which is usually there's a gain in the transfer function. So if you have a gain in the transfer function k, then when you take the log to the base 10 of the gain value, that's a constant value, and you multiply that by 20. So that's going to be a straight line at all the frequency values over which you are plotting the Bode plot. If you have a real zero in terms of 1 plus j omega over omega 1, then the Bode plot of the magnitude will simply be 1 plus omega over omega 1 square root of that, what is the magnitude of that, and we do some approximations because again Bode plot is an approximate plot, and the approximation is that if omega 1 is quite less than omega, then we ignore this term and we assume that 1 is predominant and log of 1 is 0. So up to omega 1 we assume that the Bode plot of this factor is 0. And when omega exceeds omega 1, then we assume that 1 is negligent, and it will simply becomes 10 log omega over omega 1 square, or 20 log omega over omega 1. And in that case, as omega increases by 10-fold of the frequency, then this value increases by 20 decibels. So we say that the Bode plot is increasing 20 decibel per decade for any zero, which is not repeating. If it is repeating, then of course, it increases by whatever the number of repetition is times 20 log of omega over omega 1. Like as Bode plot of the pole, of any pole, up to omega, it is 0, and after omega, it drops by 20 decibel per decade. If you have repeated poles or repeated zeros, then if you have zeros, it increases by whatever repetition of the root is, and we're talking about the real root over here, whatever the repetition of the zero or pole is, times 20 log of omega over omega 1 if it is 0, and negative of whatever the repetition is, times 20 log of omega over omega 1. So the slope of the line increases by repetition times 20. So if it is repetition of 2, then it's become 40 decibel per decade. 3 is going to become 60 decibel per decade, and so on and so forth. We went over example, draw Bode plot. We did this problem, an example circuit, and we solved the circuit for the transfer function, output over input. And you know what, in this transfer function, I should have just started with, instead of going into j omega domain, I should have just kept this into S domain. And I think that the equation might be much easier, and then in the last step, I should have just put S is equal to j omega. I just made a mistake. Then I started solving in j omega domain. But anyways, I think we had a little issue in this problem. I didn't go back and check. Our values somewhere might not be correct. But assuming that this is our transfer function, then based on that transfer function, we created the plot. We had 3 factors or 3 parts. We had 1, 0, and then we had 2 poles. And based on that, we went ahead and we created the Bode plot of this. Which was something like this. So we have a constant gain, we have a 0, and then we have 2 poles. And then when we added all of them together, then we got this response. This is something that the project that I have assigned. So this is something that you're doing in that project, not exactly this problem, but it's a generic project in which I'm asking you to enter the gain, for example, 1000 as the gain, then your 0. So if we go back to the last one, if you go back and call this j omega, of course, s, then you're gonna enter your 0, which is, the 0 is s, so 0 basically. And then you're going to enter your poles for these, so 10 and 20,000. And once you enter those inputs, then your project should create these dotted lines to show each of the item, each of the Bode plot corresponding to each of the factor, and then add all of these to give you the Bode plot. So that is a project, of course. We can discuss a little more if you want later. But I showed you an example also. And that example actually was based on this problem that we did last time. That is, your gain is 200. One of your 0 is, you can put negative 1000 as one of the zeros, or 1000, whichever. In the equation it is taken as 1000, of course, s over 1000. And then you have 2 tens and 100 as poles. So this is what I tested. I tested many functions, but this is what I gave you as the example in that file that I provided for the project number 2. So you will see that you're gonna get this Bode plot. Now I provided you two different outputs. Hold on 1 second. I provided you 2 different outputs. And in those outputs, the first one is when I'm plotting, let me go back. I'm plotting 20 log 10 right here. So I'm plotting each one of them separately. 20 log 10 omega over 10, 20 log 10 omega over 10. I'm plotting each one of them separately. The dotted lines. So 2 dotted lines are going to be overlapping with each other, which will be 10, and then the slope is going to be 20 decibel per decade. And then there will be another line, the same line on top of that. So that's, you will see in my first output example. But when you add all of them together, it will still give you the correct Bode plot. In the second, so if you do up to that point, then you get basically 80% of the point. In the second graph that you will see, I am plotting 40 decibel per decade, negative 40, when the roots are repeated. These 2 roots, I'm plotting negative 40 decibel per decade. And that plot is similar to this plot, which you see over here. So work on the project and see if you can make it work. I would like you to make it work, up to this one, which is the last example, so you can get full 100% point. But even if you make it work, the first one that you see, still you're gonna get maximum 80% of the point, so that shouldn't be a bad. If you have any question about that project or Bode plot to this point, because this is the last thing I believe we discussed last week, and we're gonna start with phase, and then we're gonna move on to the second order Bode plots. and do a problem or something, I guess, in the meantime. So if you have any question up to this point, please go ahead and ask. And give me 1 minute. Let me see. Somebody was calling me. Give me 1 minute. Okay, if there is no question, let's move on to the phase Bode plot. So how do we draw phase Bode plots? Again, remember, approximation is what Bode plots are. You can always create the exact plots versus frequency, whether it is whether they are the phase plots or magnitude plot. So you can always do the exact one. The reason we do a Bode plot is that they are faster way to estimate the response of the frequency response of a system in terms of approximations. So once again, what are the approximation for the phase Bode plot? So if you have a single order pole or single order zero, your phase Bode plot for zero, remember the magnitude for this is going to be square root of 1 plus omega over omega naught square, and the phase of this is going to be arctan of what you call 1 arctan of real part over imaginary part over real part. So omega over omega naught divided by 1, and of course I'm not showing you divided by 1. So arctan of omega over omega naught. And remember, once again, this is to show you the equation or expression for the magnitude, as we discussed earlier today as well, and perhaps sometime earlier as well. If you're just using arctan function, A10 function, MATLAB or calculator, you have to be careful if the point is located in the second or third quadrant, because the angle is not going to be correct if you use arctan. If it is in the second quadrant, you will have to add 180 degrees to get the correct angle. And if the point is located in the third quadrant, then you have to add negative 180 degrees to get the correct angle. Again, if you are using angle function in MATLAB, or if you're using A10 in MATLAB, y comma x, if I remember correctly, then, and this is just a complex number, x plus jy, then of course it's going to give you the correct angle phase, and both are going to give you phase in radians, not in degrees. I believe A10 also have A10D. I'm not really sure. Let me open my Octave and check. It doesn't look like it has A10D, so A10D -3, comma, -2. No, A10D is working because it is giving me a phase in the third quadrant, which is 123. So A10D basically is going to give you phase in degrees instead of radians. So that is also there. For some reason, it is not showing me in the help, but A10D also exists. Of course, angle function always give you phase in angle in radians that you will have to convert into degrees if want. Okay, anyways, so what is the approximation? The approximation is if omega is less than 0.1 omega naught, so 1/10 of omega naught. If omega is less than 1/10 of omega naught or omega c, whatever you want to call it, cutoff frequency. I think c will be better. Omega naught represent resonant frequency, so omega c is a better term. cutoff frequency. So if omega is less than 1/10 of omega cutoff, then we take that omega over omega cutoff is 0, and the phase, of course, is going to be 0. Arctan of 0 is 0. And if omega is greater than 10 times the cutoff frequency, then we assume that omega over omega cutoff is very large. I'm showing you infinity. Let's say it's heading towards infinity. And if you are taking arctan of a very large number, that will be 90 degrees. All right, who's going to tell me why arctan of a very large number is 90 degrees? Somebody? Anyone?
Is it because it becomes basically a vertical line? There's an asymptote somewhere.
Say it again. I think Nicola, you were saying, right? You're talking. I don't even know who's talking. Nicola, you were saying something.
Yeah,
okay.
It's me.
What did you say?
I thought that at some point you're approaching infinity
because
there's an asymptote. So the highest. I may be wrong.
Or you may be right. If you explain it clearly, then I can understand. You're saying we are approaching infinity because of what?
So the tangent at some point, when the angle is 90 degrees, the tangent is a vertical line.
Yes.
So if you have a very high number, you have a vertical line.
Okay.
And you're approximating 90 degrees, but it's actually not 90 degrees. Otherwise, it would be the asymptote.
Yeah, if it is 90 degrees, it does not exist on 90 degrees. But as you are going towards 90 degrees infinity. So again, I think you're right. Your explanation is right. But the explanation is very simple. Well, remember, tangent represent your slope anyways. But if what is tangent? Tangent of x is sine of x over cosine of x. So your phase x, as you are going towards 90 degrees, sine of 90 is 1 and cosine of 90 is 0. So basically, this is approaching towards 1 as you are heading towards 90 degree, and this is approaching towards 0. And that's why as you approach towards 90 degrees, the number starts getting bigger and bigger and bigger. At 90 degrees, of course, it's not going to exist because 1 over 0 it does not exist. But as you're approaching 90 degrees, then you are going towards, your number is going to get bigger and bigger for tangent of 90 degrees. Tan 90 does not exist. But tangent of 89.9999999, that's going to be as close to, let's say, infinity as possible. And that's why anytime you have the arctan of a very large number, that is 90 degrees, or if it is on the opposite side, that's going to be 270 degrees. And when omega is equals to omega c cutoff frequency, then arctan of omega over omega c, arctan of 1 is 45 degrees. So the phase of h omega is 45 degrees. And same thing we use for single order pole for this, except the phase are different, negative instead of positive. Someone is going to tell me why it's going to be negative instead of positive. That is 0, negative 90, and negative 45 for these conditions. Anyone? Now, over and over again, it just goes back to the complex numbers, remember. If you have the basics of complex number, clear basics, then these questions are very easy. So we discussed the conditions for the phase of a 0 right here. And I'm not discussing poles, but I'm saying that it's going to be the same conditions, except, so it's going to be the same condition like this, except your angles are going to be negative. This will be negative 90 and this will be negative 45. Anyone want to tell me why?
So subtraction from the inverse tangent of numerator minus.
Yep, when you're
calculating to a negative.
Yeah, when you are determining the angle of this pole, the angle of this pole is going to be the angle or phase of the numerator minus the phase of the denominator. So that pole h of j omega is angle of the numerator, which is 0. Angle associated with 1 is 0, 1 on the real axis. We discussed this morning as well. And then angle of the denominator, which is tangent inverse of omega over omega c. So it's the same thing as this, except it's negative tangent inverse of omega over omega c. And therefore, all these angles are going to be negative. Negative 90, 270 degrees that is, and negative 45 when these conditions are met. Okay, so let's do an exercise. The same control system that we have here, with the same transfer function, this 200 s plus 1000 s plus 10 square s plus 100. So it has 1 zeros and 3 poles. 2 of the poles are repeated, 1 pole is single. And we have to draw the phase Bode plot for that system. Again, we're going to look at each one of them separately to draw the phase Bode plot. So the first thing is 200, of course, that's 0. The phase associated with a constant value is 0. Now, if it is negative 200, let me ask someone, if it is negative 200, what will be the phase of that? Let me delete that, just ask you a question. So I'm going to write this down in terms of cutoff frequency. And this is 1000. So to draw the Bode plot, whether it's a magnitude Bode plot or phase Bode plot, first you're going to convert this into the standard form, which is gain times the pole, which is, now this is called the single order pole. So 1 plus the frequency over the cutoff frequency. That's also single order pole, but it's repeated. So 1 plus j omega over 10 is square. So either you describe like this, separate or square. So earlier I come to my question. So if you are doing the phase Bode plot of this, now phase of the numerator minus phase of the denominator. And if you have product, then the phase adds. If you have division, then the phase subtracts for complex number. So you have basically phase of this constant value. We don't have to show that. What is the phase of this? 20. Edmund, you were saying something.
Is it 0 degrees?
0 degrees, of course, it lies on the real axis, is 0 degrees, exactly. Now phase of this is plus arctan omega over 1000. And then phase of the denominator. So in the denominator, both the phase are going to be added together. And then it's going to be subtracted when you write it down. So that's going to be phase of, so it's going to be phase of this plus phase of this. And both phases will be same. So you're going to add them together. Let me write down separately and then we'll add them together. A tan omega over 10 minus A tan omega over 10 and minus A tan omega over 100. So we have A tan omega over 1000 minus 2 times A tan omega over 10. So if you have a square, then basically it's going to be 2 times the phase of this element. If you have a cube, then 3 times the phase of this complex number. That will be your phase expression for this transfer function. So observe, phases are simply addition and subtraction, similar to if you are doing the magnitude Bode plot, which is of course in decibels, then it just becomes addition and subtraction instead of multiplication and division. Now phase is always addition or subtraction of a complex fraction. It's not multiplication or division. Going back to my question, I asked you earlier, what if I have negative 20 instead of 20? What will be the phase of that negative 20?
Would it be 180 since the
180 degrees, exactly, Catherine, very good. It's going to be 180 degrees because negative real numbers on the complex plane, they lie on 180 degrees or negative real axis. So this is the complex plane, j omega, negative j omega, real, and negative real. So if it is negative 20, it's going to be on this axis, and that will be 180 degrees from the real and from the positive real axis. So it's going to be 180 degrees. So you'll have to put down 180 plus A tan omega over 1000 in that case. Similarly, if you have a point on the imaginary axis, J2, J3, J4, whatever, the phase, of course, is, so if it is J2, then in polar form, it is simply 2 angle 90 degrees. So magnitude is 2, and the phase is 90 degrees because it is on the j omega axis. And likewise, if it is on the negative j omega axis, the phase is negative 90 degrees. Magnitude, of course, is going to be whatever the magnitude is there. So again, keep these small things in your mind because these are very simple, but they can lead you to make mistakes, as I've seen many, many times. So this is our equation for the phase response. So how the phase response is going to be over, let's go ahead and insert another slide. Just insert a blank slide. How the phase response is going to look like. Move this on the side. Okay. So this factor is going to be 0, phase of 0 until omega, and then until 1/10 of 1000, which is 100. So until 100 radian per second, this is going to be 0. And when it will become 10 times the cutoff frequency, 1000, then it's going to become 90 degrees. So what I'm going to do, I'm going to go ahead and create the axis like this. Phase of j omega. And I'm going to do 45 and 90. 45, 90, 135, 180, and so on and so forth. And my frequency in logarithmic scale, radian per second. Let's say this is my 1. This is 10. 10,000. That should be good enough. So the first one is 8n omega over 1000. Now remember, the approximation is that omega is less than 1/10 of omega c, phase is 0. Omega is greater than 10 of omega c, phase is 90 degrees, because this number is going to become too large. So 1/10 of 100 is going to be 10. So up to this point, the phase is 0 for the 0 factor. And at 1000, phase is going to be 90 degrees. At 100 is going to be 45 degrees. So this is for the factor phase of 1 plus omega over 100. Then we have -2 a10 omega over 10. Okay. So now this one, as long as omega is less than 1/10 of 10, that is 1, your phase is going to be 0. And when it will become 100, that is 10 times 10, the phase will be 90 degrees. And at 10 is going to be 45 degrees. And we have -2. So when we do -2, so 2 times 45 will be 90, and 2 times 90 will be 180. So the phase is going to go from 0 to 180. And at omega is equal to 10 radian per second, it's going to be 90 degrees. And of course, we have the negative sign. So all the angles will be negative. So at 10 is going to be -90. At 100, it's going to be 180. And since I'm starting at 1, which is 1/10 of 10, so all the values before that are going to be 0, 0.1 to 1. So this is my phase of 1 over 1 plus j omega over 10 squared. Guys, make sure if you have any question, please ask. And the last one is 8n omega over 100. So if omega is up to 10, it's going to be 0, and that at 1000, it is going to be 90 degrees. And it's a pole, so it's going to be negative values. I believe I made this incorrect because that was 1000, right? That was 1000. So it's going to be go to 100 and then 10,000. Let me do this again. The 0, I made it incorrect. Since it was 1000, I put 100. That's 1000. That means up to 100, it is going to be 0. And then at 10,000, it's going to be 90 degrees. And at 1000, it's going to be 45 degrees. Then I have a pole 1000, that means up to 100, it is going to be 0. Up to 100, it is going to be 0. At 1000 is going to be negative 45 degrees. And then at 10,000 it's going to be 90 degrees. Wait a minute, it's going to be 10, sorry. So up to 10 is going to be 0. At 1000 is going to be 90 degrees, negative 90 degrees. And at 100 it's going to be 45 degrees. Because you have slope is different than this because so this is, if you show your slope, this is what is that, 45 decibel per decade, 45 degrees per decade slope. This is negative 45 degrees per decade, and this is negative 90 degrees per decade. So these are the individual lines for corresponding to each of the factors that you see here. 3 lines for 3 factors, phases. And of course, your cumulative result is going to be the sum of all these angles. So you start at 1, you have this line going down. So your line is going to go down up to 10, this point, with a slope of negative 90 degrees per decade. Once you get to that point, then you're going to add the phase of this into phase of this as well. And that's going to be an even steeper slope. It's going to negative 45 and negative 90 is going to drop down with negative 135 degrees per decade until it will hit negative 90 and negative 180, 270 degrees. So it's going to hit 270 degrees. Let's do this. Let's go down. $180 plus what we are doing, 45. So that's negative 225 and then negative 270. So it's going to hit this line right here. And your slope is going to be even faster. So from 10 to 10 to 100, and then what is that? It goes to up to 100. Okay. So it's going to be 10 to 100 is going to be negative 45 decibel. And then after 100, its slope is going to be again this until it will hit negative 270 degrees. Actually, at 100, it is increasing. So I'll have to go back and fix it. So at 100, this is start increasing 45 degrees per decade. At 100, this one decreasing negative 45 decibel per decade. That is going to cancel each other. I didn't realize it. So from 10 to 100 is going to drop by negative 135 degrees per decade. So that means it's going to go from negative 90 and 135. That's going to be 225. So it's going to reach 225 actually. 225 up to 100. And at 100, this slope and this slope will start canceling each other. And you have and actually this all will cancel each other, 90 degrees, 90 degrees. So these two will start canceling each other, and you will have just 225 degrees that will be left. And that's going to be your final phase for all frequencies.
Is this the final? I thought the green one goes one more.
Yeah, so we have these two angles are going to cancel each other, right? After 100.
Yeah, but the yellow one will plateau at 1,000, but the green one keeps going until 10,000.
Oh, okay, I see what you're saying. Right. So they start canceling each other at this point, and then this is going to become negative 90 degrees. So you have negative 90 and 45. So that's going to be negative 45 degrees. So yeah, it's going to go to negative 270. And then at 1,000, at 10,000, these two are going to cancel each other, and only whatever is left is going to be. So yeah, it's going to go to most likely negative 270. It's always confusing. The phase plot is usually confusing, more confusing than the magnitude plot. Let's see. Okay, let's look at it again. So at this point, you have only this line. At 10, it starts dropping up to 100. And this is dropping up to, this is also 100, I'm assuming. So this is dropping 100. So these two are going to add together. That's negative 45 and negative 90, negative 135. So up to 100 is going to go to negative 225. And this is going to become negative 180 degrees. And this is still dropping 45, but this is increasing 45. So they are going to cancel each other. So I'm going to go to 1,000 with negative 45, I believe, negative 225. And then this is going to plateau negative 90 degrees. But this is increasing. So if it is negative 90 and positive 45, that's going to be 45 or negative 45. So negative 45 and negative 180 will still be negative 225. So it's going to go negative 225. I think it's going to be negative 225 all the way. Let's see. At this point, you have 45 degrees. This is negative 90 degrees. And this is negative 180 degrees. So 90 minus 45. 45 minus 45 is 0.
That's 45 minus negative 90.
I'm sorry?
That point is 45 degrees and then negative 90.
Negative 90, so that's negative 45. And that's negative 180, so it's going to be 220, negative 225. Now, if we go further beyond to this point, then you have, so this is now you have negative 90 degrees, and this is still increasing up to 90 degrees. So this is negative 90 and 45, negative 45, so this is 225. So you're saying it's going to go down a little bit, and then it's going to go to 270. Let's see. And so this is negative 90, and minus 180, 270.
Shouldn't it end at negative 180? Because it should go back up from negative 225 to negative 180 when the negative 90 degree line plateaus.
Let's see if that's the case. So negative 90 minus 180, negative 270, and negative 270, you are adding phase. So when it gets to this point, it's going to get 90. So this 90 and negative 90 will cancel each other, and you have negative 250, negative 180 left. So yes, it's going to increase up to 1 exponent 4, and then it's going to plateau at negative 180, right? So this is going to be, what was that, 90, negative 90 degrees. That's going to be negative 225 degrees. And that's going to be negative 180 degrees, yeah. And the slope is going to be 45 degrees and 90 degrees per decade, 45 degrees per decade. So negative 45 degrees per decade, negative 135 degrees per decade. And constant value, negative 225, 45 degrees per decade, and negative 180. So now let's see if we get the same, if we plot it using MATLAB. So let's say S is equal to omega is equal to, we're going from, let's say 1, we can go from 0.1 to see it properly, but or we can go from 1 to 1 exponent 5, let's say 1 to, and then we have H is equal to S is equal to I times omega, and H is equal to 200 times S plus 1000 S plus 10 square S plus 100. That's my transfer function. Of course, I took S is equal to j omega. Omega I'm defining from 1 to 1 exponent 5 with an interval of 10. So let's do phase of H is equal to angle of H times 180 divided by phase. And this is going to do the exact phase, remember. It's not going to be approximate because I'm plotting the exact using angle function, but it's going to give us an idea as what will be the last value and everything. The same A log x omega phase of H. Okay, well, this is showing pretty strange phase. Let's see. That doesn't look very nice. Let me see. 200 times S plus 1000, S plus 10 square, S plus 100. That doesn't look right. Oh, it might be showing the discontinuity at. All right, so it is going down. Yeah, this is not right for sure. Let's say Bode. Use Bode. Function is the same, right? 200 times S plus 1000 and divided by S plus 10 square S plus 100. Okay. All right, let's do this then. Phase of H is equal to, what do we have? Equation. All right, so we have omega over 1000. So we have 8 and 2D omega comma 1000 minus 2 times 8 and 2D omega 10 and minus 8 and 2D omega over. Actually, in this case, my y is this, and my x is 1 actually. So let's do it right. X is 1. X is 1. Let's see if this will work. Semi log x omega comma base of h. All right, that looks a little better. Similar to what we got, I guess. Of course, it is exact. We got approximate. So start going down, and it becomes steeper at 10, as we have becomes steeper at 10. And then, of course, you have a curve over here. We are not showing any curve because, again, ours is approximate. This is exact. And it's going to go down to 225 to 30, whatever the angle is. And then it's going to go up again and going to go to negative 180. So, yeah, our approximate curve is correct. And this is the exact one, as you can see on the screen. This is the exact. And this is your Bode plot, which is approximate. So you can do both of them. I wonder why the phase function is not plotting it properly. That's strange. Phase of H, angle of this. Square times S plus 100. The equation is correct. It's strange. I'll see why it is not doing it correctly. But yeah, this is plotting it correctly as according to what we have. Of course, it's exact, as I said, not approximate. So we can go ahead and put this as well. Edit. Copy figure to keyboard. And insert slide. Phase plot. All right, guys. So again, so far we are only discussing the first order system. There is no second order root. But so this is the phase plot. This is how you're going to do the phase plot. And again, you can always do the exact instead of approximate. But approximate, remember, is the Bode plot. Exact is not really the Bode plot. It's the exact plot, magnitude versus frequency or phase versus frequency. Bode plot, of course, are the approximate plot. Any question that you may have?
So for the project, we do the approximate, right? Not the exact.
So for the project, you are only doing, first of all, magnitude plot, and it's Bode plot. So that's why you are doing approximate plots, not the exact plots. If I open the project, so magnitude Bode plots. You don't have any complex zeros or poles. We're going to discuss complex zeros and poles today. Poles specifically, zeros are going to be opposite of that. So you have a generic transfer function. All of these are real zeros. All of these are real poles. So you're going to ask user to enter the gain value. You're going to ask user to enter the zeros, z1, z2, z3 as a vector, then p1, p2, p3 as a vector. You're going to define the range W over which you want to plot it. And then define the range of W from starting from 1 radian per second up to 100 times the highest cutoff frequencies that you have from either zeros or poles. Because again, as you saw, we have to go we have to go up to higher frequencies. So my highest frequency here was what was that, 1000? Well, this is phase. So if I go to my magnitude Bode plot, in this my highest frequency was, cutoff frequency was this, I guess, 10,000. So go 10,000 times 100. So one mega in this case. So you can plot everything clearly. So that's the range of omega that you're going to define, 10 times the highest frequency, whichever pole or zero, whichever is the highest. Then you're going to calculate the corresponding value of gain in decibels. Remember, this equation is going to be written as this. S will be j omega, remember. But you're going to write down in the first order form, 1 plus frequency over cutoff frequency. So this will be your modified gain value right here. And you're going to calculate the magnitude in decibel for this modified gain value. And that is going to be valid for all the frequencies range that you are defining, the whole frequency range. So create it as a vector. Well, as I said, create as actually as a matrix. So the first row of the matrix is going to be this value. All values will be same. That's going to be the first row of the matrix. And next, you're going to calculate the Bode plot corresponding to each of the zeros. So you're going to use the same criteria. That is, up to omega is equal to z1. The magnitude will be 0. And as omega is going to exceed z1, then the magnitude is going to be calculated as 20 log base 10 omega over omega c for each one of them. So for when you calculate, when you define, calculate the vector for this, that's going to be the second row of the matrix. It's the same matrix where the first row is this. Then this will be the third row of the matrix and the fourth row. And why I'm saying keep the same matrix, because if you have the same matrix, then when you are updating the matrix and adding each row, that's easy to do using for loops actually. And then you're going to do the same for the poles. Up to P1, up to P2 for each vector is going to be 0. And when will it will increase beyond P1, then the value is going to be negative 20 log 10 omega over omega c. So you're going to update that matrix. Each row is going to correspond to each vector. And once you have the whole thing, basically, then you add all of them together, all the columns together, you're going to get the Bode plot basically. So you can plot each row of that matrix individually using the dotted lines. That's going to be the Bode plot corresponding to each vector. And then you can plot the added value of each vector. When you add a matrix, then it's going to add all the columns basically. That's going to be your Bode plot, and you can plot that using a thicker line to show that it is the sum of all of it. If you do that, you're going to get curve like this. So this curve is basically, where is it? Which one was that? No, not this one. This one. So this curve is this, because it's the same function that I'm using. So you will see curve is the same. You have whatever gain is there, then it's going to drop by -20 decibel per decade, then -40 decibel per decade, and then again -20 decibel per decade, which is -40 decibel, -60 decibel, and -40 decibel. So that's how it is decreasing. And now these two lines are overlapping. This is S plus 10 and S plus 10, two factors. So those two factors are overlapping. So two of the lines from my matrix. So I'm not showing what you call this -40. I'm showing this as -20 decibel twice overlapped ones, because again, we have two factors which are the same. The 10 factor, this factor. But if you move on to the next one, then in this one, I'm showing that this is -40 decibel per decade. This is -20 decibel per, -40 decibel per decade. This is the other line, cutoff frequency is 100, which is dropping -20 decibel per decade. And this is a 0, which is increasing by 20 decibel per decade at 1000. And the final result is still going to be the same. Bode plot is still going to be the same. But the individual lines are different, because in this one, I'm showing you the -40 decibel. That is a square real number. In the last one, I'm not showing you that, but this is the separate 10 and 10 plotted separately, which will be two lines overlapped on each other. So if you get to this point, you got 80% of the grade. And if you get to this point, for this, I mean, I can, you can have whichever function you want, but this is just for the testing purpose, because we also did that in the class. I can have 3 tens values. That's going to be -60 decibel per decade slope, and accordingly, the plot is going to change. So not difficult. Up to this point, it's not difficult, actually. It's pretty straightforward. This point, the way I did it, it took me a little while. And then I started thinking, I think I would have just used the same matrix that I developed here, and then I could have done it from that matrix as well. So, but anyways, I mean, that's the programming. The way you'll create logic, sometimes it takes longer, and you create more complicated logic, and it might be a simpler way to do that. And I realized after I created a little more complicated logic that it could have been done a little simple way as well. But anyways. So yeah, this is the project. So each individual line should be there. And then the final Bode plot, which is the sum of each individual line, is going to be the Bode plot. So this is what the project is. So it's not exact, remember? It is approximate. That is why it is the Bode plot. All right, any question about this before we take a break? And then after the break, we are going to discuss the second order systems, Bode plot of the second order systems, and the phase Bode plot as well. And then there will be a summary of Bode plot. There's one more example. Any question about anything, guys, so far? Of course, next week is our last class. I will see if I can do 1 or 2 design examples, practical design examples, and then we can do review. Because I don't think today, I did not put any design example by the way today, but I don't think we'll be able to do any design example today, because 1.5 hours left, and I think by the time we'll finish is going to be by 8:15 anyways. Okay, if you, by the way, I know more people took the DSP student feedback of instruction since I asked you to take it in the class. And I think 9 students at least took it. If you did not take it, please take the SFI survey. For this class, I think only 1 student has taken SFI. So please go ahead and take the SFI survey student feedback instruction for this class as well as other classes you're taking. But make sure you take the student feedback instruction. It's going to close, I think, on 29th. So there is still some time, but just take it as soon as possible. We're going to go ahead and take about, let's say, about 10-minute break, and then start discussing the second order systems. Guys, we're going to go ahead and start back. So guys, second order system, if you have a complex conjugate root, whether it's in the pole or in the zero. And generally we look into the zeros because the zeros define the transient characteristics if you have the complex conjugate pole in the transfer function. So magnitude Bode plot, and then we're going to look at the phase Bode plot if you have the second order system. So the general expression of the second order system, as we have discussed before, is s square plus 2 zeta omega n s omega plus omega n square. Zeta, of course, is the damping coefficient that goes from 0 to 1, and omega n is the natural resonant frequency. And this defines an underdamped system. And the characteristics of underdamped system is that the response is exponentially decreasing sinusoidal response. So the frequency of the sinusoid is omega n, and the time constant of the decay is defined by the damping coefficient. Actually, the time constant is, if you remember correctly, 1 over zeta omega n. That's the time constant with which the exponential function is going to decrease, and omega n is the frequency of the decay. And the response curve, of course, is simply something like this. So that's the second order system that produced this type of output. A stable system we're talking about, of course, that the response is decreasing, transient response, rather than increasing. So if you have that type of vector in as a pole or a zero, let's discuss the pole because that's is more common. But in general, if you have that type of vector, then when you put s is equal to j omega, it's going to be j omega square plus 2 j2 zeta omega n omega plus omega n square. When you put s is equal to j omega, you pull 1 over omega n out, and you can write the rest of the equation as shown. J omega over omega n square, which is coming from s square, plus j2 sigma j2 zeta omega over omega n plus 1. If you put that's going to be not 1. Actually, let me see. We are pulling, that's going to be omega n. Why did I put 1 over here? All right, let me see it again. Yeah, that's going to be omega n. This is omega n square, so we divide the whole equation with omega n. So you have j omega square. Actually, we're pulling 1 over omega n square out. That's why I did that. Yeah. So that should be 1. That's correct. Okay. So we take 1 over omega n square as we divide the whole thing by 1 over omega n square. We take it out, not divide it, but we take as a common factor out, basically. So we have the real part of this equation, and we have the imaginary part of this equation. This equation can be written as constant 1 over omega n square. That's going to be square. Will be contributed towards total gain of the system. Let's concentrate on the quadratic factor, j omega over omega n square plus 2j. Okay, so we can write this down. J square, of course, is -1. So omega over omega n square, negative omega over omega n square, 1 plus j2. So we have the real part which is 1 minus omega over omega n square. That's the real part of the equation. And then when we have the complex or imaginary part, which is j2 zeta omega over omega. So you have a plus jb. We consider u to be omega over omega n, just so that we don't have to keep repeating omega over omega n and replace it or substitute it by a variable u. So we can go ahead and write down this expression as 1 plus j2 zeta u minus u square, which is right over here. Or the real part is going to be 1 minus u square, and the imaginary part is going to be 2 zeta u. And if we calculate the magnitude Bode plot, and if we assume this is a pole, that is, it's in the denominator, 1 minus u square plus j 2 zeta u, then for the magnitude Bode plot, we're going to get negative 20 log of 10, and the magnitude of this, which will be square root of a square plus b square. So remember, this was a plus j b. Negative 20 log 10 of a square plus b square. Now the approximation, because remember, Bode plot is an approximate plot. So what is the approximation? If omega is quite smaller than omega n, or u is quite smaller than 1. Because if omega over omega n, which is u, if omega is quite smaller than omega n, and that will become u is quite smaller than this factor 1. Then we assume that this factor is negligible, this factor is negligible, and we assume that the magnitude response is going to be 0, which will be negative 20 log 10 of 1. The next approximation is if omega is quite larger than omega n. Then we assume that u square is the dominant factor. So this factor 1 minus u square, if u is quite larger than 1, or if omega is quite larger than omega n, that means u will be quite larger than 1. So it's going to become negative u square, which will be u square. And we assume that this will be the dominant factor. So we ignore every other thing. We ignore this factor and we ignore 1. That means that your slope is going to be negative 20 log 10 square root of u square, or simply u square. That will become negative 40 log 10 of u. Negative 40 log 10 of u. This is u. So it's going to drop by 40 decibel per decade. So if you're plotting this, you have an asymptote. Asymptotically, it's going to reach. So let me show that. So if you have a second order, and let's say this is omega n, then we have one line like this, and then we have one line like this. And this slope is negative 40 decibel per decade. But we make some modifications to this around omega n, right over here. Because the two conditions are omega has to be quite smaller than n, so it is not going up to omega n exactly. We still have to keep it quite smaller than omega n. Generally, we can keep it like 1/10 of omega n is okay, or 1/20th of omega n. And when omega is quite larger than omega n, so again, it's not at omega n, but it's larger than omega n. Let's say 10 times omega n, or 100 times omega n, or 20 times omega n, whatever. What's going to happen around omega n? So when omega is omega n, that is u is equal to 1. U is equal to 1. The response will be negative 20 log 10 of 2 zeta. So if you look at this expression, when omega is equal to omega n, u will be 1. So 1 minus u square will be 0. This will be 0. This u will be 1. So it's going to be 2 zeta square. Square root of 2 zeta square is going to be 2 zeta. So your gain is going to be negative 20 log 10 of 2 zeta. So whatever the value of damping coefficient is, based on that value, you will evaluate the value around omega n. The difference between the actual magnitude curve and the asymptotic one, which I'm showing you, is a function of the damping ratio and must be accounted for when zeta is less than 0.707. So for different values of damping coefficient, if we plot the curve of second order Bode plot, and these are pretty much the exact plots actually from the book, then this is what you're going to get. So this is negative 40 decibel per decade right here. Asymptotically is going to negative 40 decibel per decade. This is your 0. And then close to omega n, it is going to rise up, going to a peak value, and then asymptotically merging into negative 40 decibel per decade. So remember the step response of a second order system. If you remember, you had, of course, a peak value, and then it used to settle down. So that peak was there for the second order response of the step response of the second order system. So similar to what we studied earlier, you will have a peak value around omega n. Now the peak value will not be at omega n, or it may not be at omega n exactly. Actually, peak value is going to be at the resonant frequency, omega r. And the resonant frequency is given by omega n square root of 1 minus 2 zeta square. If you look at these curves, and this is plotted against u, that is omega over omega n. So when u is equal to 1, which is right over here, omega is equal to omega n. So observe, when zeta is 0.05, then omega n is approximately where the peak is. When zeta is 0.1, actually peak is happening before omega n. Likewise, when it is 0.5, peak is happening before. 0.2 peak is happening before. So omega r, in fact, the resonant frequency is in fact smaller than the natural resonant frequency. If zeta is less than 0.707, because if you put 0.707 over here, you're going to take the square, it's going to become 1/2. And 1/2 and half will cancel each other. It's going to be 1. So when zeta is 0.707, then omega r resonant frequency is going to be 0. As zeta approaches 0, very small value, then the natural resonant frequency and the resonant frequency are going to be close to each other. If you remember from your circuit analysis, the difference between natural resonant frequency and frequency, let's say for RLC circuit that you discussed over there, anybody remember? Let's say for parallel RLC circuit, what is the resonant frequency and what is the natural resonant frequency? Anybody remember that? So your Napier frequency, forgot what the variable we used to use, alpha. For parallel, I believe it's about 1/2 RC, radian per second. Your resonant frequency, omega naught we used to call it, here we're calling it omega r. Your resonant frequency used to be 1/LC. And when you used to put the two roots, S1 and 2, negative alpha plus minus square root of, I believe, alpha square minus omega naught square. Is that? I don't know if I forgot if that's, I believe that was it. So if alpha is greater than omega naught, then you had the overdamped system. If alpha is less than omega naught, then the square root is going to be complex value. And that used to represent the natural resonant frequency, negative alpha plus minus j omega n, where omega n is omega naught square minus alpha square. If omega naught is greater than alpha, or alpha is less than omega naught. So as you can see, omega n, this was omega n basically in circuit analysis. So resonant frequency, in general, resonant frequency is the frequency at which your LC circuit tunes basically. So the reactance of L becomes equal to the reactance of C in a parallel RLC circuit. That frequency is the resonant frequency. And at that frequency, you get the peak value of the output, if we talk about circuits, that is. So anyways, so when you draw this curve, the second order curve, then, and this is the exact curve, although it's 20 log 10, but you're gonna have a slope upward basically. Not slope, sorry. You're gonna have a peak value upward for the second order system. Initially, it's gonna be 0. Asymptotically is gonna be negative 40 decibel per decade. However, as you get closer to the natural resonant frequency, your curve is gonna go up, and then it's gonna go down, and then it's gonna merge asymptotically to negative 40 decibel per decade. So that's how, as you can see, 0 to negative 40 decibel per decade, 1 to 10, that's 1 decade. So asymptotically, it's going to negative 40 decibel per decade. When zeta approaches 0, omega r approaches omega n, as we discussed. The maximum value of the gain is given by at resonant frequency. Peak value is 2 zeta 1 minus zeta square. So 1 over 2 zeta square root of 1 minus zeta square, as long as zeta is less than 0.701. So that's how you can calculate the peak value at omega r. Remember, it's not at omega n, it is at omega r, which comes just before omega n, as you can see in most of the values. But if zeta is smaller, then omega r will be very close to omega n, as you can see from this equation. So if you have a system with railroads and rail poles and second order poles, then when you're drawing the Bode plot, of course, the rail poles, we discussed how you're going to draw it, the rail zero is rail pole. If you have a second order, then you will incorporate the second order, something like this. And again, you can do approximation. You don't have to be exact if you are doing freehand. Then you can just do approximation, calculate the peak value using this equation right here. And then based on that peak value, calculate omega r value. And at that omega r, just show the peak value and then just connect it freehand. And then the final slope is going to be negative 40 decibel per decade. So you're gonna just merge in that asymptote. Of course, if you're drawing using let's say Bode function or something, it's gonna give you the exact plot, of course. If you're doing phase Bode plot of second order system, then we can write down the equation for phase using negative tangent inverse 2 zeta u over 1 minus u square. Remember, our equation was what was our equation? 1 minus u square plus j 2 zeta u. And of course, u is omega over omega n. I'm using this color. So if you calculate the phase of this, that's going to be y, and that's going to be x. So tangent inverse of y, 2 zeta u, over x, 1 minus u squared. So when u is quite smaller than 1, or omega is quite smaller than omega n, then we assume that phase is 0, because the numerator is going to be 0 if we assume u is very small, and the angle is going to be 0. When u is quite larger than 1, that is omega is quite larger than omega n, the phase is going to approach negative 180 degrees. And when u is equal to 1, then the denominator is going to be 0, or it will approach 0. That means this value is going to be very large, and tangent inverse of very large value is 90 degrees. So it's going to be negative 90 degrees. So the phase goes from 0 degrees, and at very as u approaches, when omega becomes quite larger than omega n, it's going to hit negative 180 degrees, and at omega is equal to omega n, it's going to be 90 degrees. So the phase is, if I want to draw the phase, (0 degrees) and omega n, where u is equal to 1, negative 90 degrees, and negative 180 degrees. Now this is, so these 3 points are right. So this 90 degrees, and then 0 and 180. But in the middle, if you have a second order system, if you're plotting exactly the value, then it's going to be something like that. Now these are the exact phase plots. So it's not going to be 0 all the way. It's going to be 0 as long as it is smaller than it, then it's going to start curving. It's going to pass through 90 degrees. And then it's going to go asymptotically to negative 180 degrees for different values of zeta, as you can see. So that's how the phase Bode plot of the second order system is going to look like. Again, if you're doing freehand drawing, it is hard to do exactly all these curves. So generally what we do, based on the value of zeta, if zeta is very small, we go flatter and then drop it. If as zeta start becoming larger and larger, we start curving it earlier. But really, if you're doing the Bode plot, then there is really no something like that. And that's acceptable in most of the cases. Of course, now we can always do exact Bode plots using computers. So to summarize all the Bode plots, if you have gain, then you have a constant value over all values of omega, and the phase is going to be 0. If the gain value is negative, then the magnitude will still be a constant value, but the phase is going to be negative. The phase is going to be 180 degrees. Keep that in mind. If you have rail 0, if you have a rail 0, then it is going to be 0 up to the cutoff frequency, and then it's going to increase by 20 decibel per decade. The corresponding phase is going to be 0 until 1/10 of the cutoff frequency, and it's going to become 90 degrees when the frequency will increase by 10-fold, 10 times the cutoff frequency, and at cutoff frequency is going to be 45 degrees. So this is going to be phase. If you have a pole, single order pole, rail, pole, then it's going to be opposite of the real 0. It's going to be 0 up to omega 1, and then it's going to drop by negative 20 decibel per decade. And for the phase, again, it's going to be opposite of the 0. It's going to be 0 up to 1/10 of the cutoff frequency, and negative 90 degrees above 10 times the cutoff frequency. And then the slope of this line will be 45 degrees, negative 45 degrees per decade. If you have a pole at origin or 0 at origin, so if you have 0, oops, let me change the color again. If you have j omega as one of the zeros or 1 over j omega as one of the poles, or j omega over omega c rather, if this is your one of the poles, then remember it's 0 plus 0 plus 0 plus. So if you have a 0, then the magnitude is going to be 20 log omega over omega c. So if you're starting at 0.01, or actually, if you 1 over j omega, so omega c is 1 in this case. Let's say omega c is 1, omega c is 1. Or we can keep any omega c, doesn't really matter. Omega c, whatever. So in this case, you have a line. Basically, in case of 0, you have the line going up with 20 decibel per decade from all frequencies. Basically, if you're starting at 0.1, then 1, then 10, or whatever is that. And generally, it's j omega, actually. I'm showing j over omega c, but it's j omega, because if you have j omega over omega c, then 1 over omega c becomes the gain of this. So it's generally j omega. So I'm actually, let me write it down. J omega. Because if you put j omega over omega c, then 1 over omega c can simply become the gain of the system. So that's 20 log of omega. So as omega is increasing, then it's going to increase by 20 decibel per decade. As omega, for the pole, as omega is increasing, it's going to drop by negative 20 decibel per decade, as shown in this figure. And of course, the phase is going to be 90 degrees for 0 and negative 90 degrees for the pole. And that's what it shows over here. Hard to see, but it's negative 90 degrees for all frequencies. And if you have complex poles, zeta is between 0.1 and 1, then you're going to have 0. Now, this is, again, for Bode plot purpose, it's okay. But if you are doing actual, then of course it's going to curve up based on the value. And then it's going to go down and then merge with this. Something like that. But for Bode plot, since it's approximate, we can take it like this. That is, we generally ignore the middle factor in general in this case. But this curve is important. The peak value is important to realize that this is a second order system. Otherwise, so this can very well be the plot of a pole with, anybody can tell me? Let's say this u is, of course, omega over omega n. And if I have this scale omega, and let's say if here I have 1000 radian per second, somebody can tell me, if I give you this Bode plot, then what you would tell me that this Bode plot correspond to what type of transfer function?
Would that be one that has repeating?
Okay, so what will be it?
1 second. 1 plus j omega over 10.
1 over 1 plus j omega over 1000. This is 1000, I'm saying.
Oh, 1000. So the
yeah,
10,000
square, and that's going to be the square. So it's going to be 2 roots. Because this is negative 40 decibel per decade. So that's why if you don't show the curve, it will be hard to realize that if this Bode plot is coming from the two real poles at 1000 radian per second, or if it is coming from a second order pole. So that's why it is important to show this peak for the second order root. And as I said, you can always calculate what is the peak value with the formula that we discussed. And the exact location of omega, again, exact location is not really important at this time if you're doing especially Bode plot, but at least you can put down that this will be the peak value that can be calculated using this peak. 2 zeta is square root of 1 minus zeta square, reciprocal of that. So this is a summary. Again, second order, again, it's okay, but this peak is important. And most of the time you will see a peak when you are going through the chapter of Bode plot and there will be second order system. Then you're going to see that the second order system is going to have a peak. Oh, I should have included one more example. Let's see if we can do one more example with second order system. So let's go ahead and insert. Inside. Let's just do this. I don't know what is the number. Let's see to be consistent. Find a number 8.7, maybe it's going to be 0.7. No, it's a base one as well that we draw. Yeah, okay. So this is 8.7. 8.7. Okay, so let's say now the Bode plot of TS is 2000 S plus 10 S plus 100, and let's introduce a second order system, second order pole. So S square plus let's see, omega n. Let's say if we take omega n to be let's calculate it so we know exactly. So let's say if we take omega n equals what did we take? 110. So let's say if we take 200, then of course omega n square will be 4,000. 40,000. And let's say if zeta is 0.2 and 2 times zeta times omega n is going to be 80. Okay, so let's do this. S square plus 80s plus 40,000. S square plus 80s plus 40,000. So in this case, of course, I did the calculation with my, so this is This is 2 zeta omega n, which is 80, and this is omega n squared, which is 40,000. So omega n, I took 200. So 200 times 200, 2 is 400, and 400 times 0.2. I took zeta to be 0.2. Is 80. Okay, so let's see if this transfer function is given to you. And we can write this down. As so hold on. So I have TS is equal to 2000 times 10 as 1 plus S over n divided by 100, 1 plus S over 100. And then here we take omega n squared as a common factor. So we take 1 over omega n squared and write this down as 1 plus S squared over omega n squared, which is 40,000, plus 2 zeta omega n over omega n squared, so 0.4 over 200 S no, 0.5 times 200. Let's see, omega n squared. We're taking omega n squared as a common factor. I keep forgetting it. So that's going to be I have to go back and check. 0.2 over omega n. Right over here. 2 zeta S over omega n. So, you know what? I may have made a mistake over here. Let's see. Oh, you know what? I made a mistake over here. It's not 1 over omega n squared. It's omega n squared that we are taking out. Omega n squared, not 1 over omega n squared. Omega n squared. And that's going to be omega over omega n squared, omega over omega n, and then plus 1. So not omega 1 over omega n squared, or omega n squared. So we're going to take out omega n squared over here, which is 40,000. So 1 plus S squared over 40,000. And then you will have 2 zeta omega n, so 1 omega n, so it's going to be divided by 1 of omega n. So okay. All right, so omega n is 0.4 over 200 S and plus 1. Okay. Oh, 1 is already there, so this is addition. And when you put T of j omega, that's going to be 20,000 times 10 over 100 times 40,000. That's my modified gain. And then I have 1 plus j omega over 10, 1 0, 1 real 0, one real pole, j omega over 100, and one second order pole. That's going to be one minus, so when I put j omega over here, that's going to be negative omega square. So 1 over omega over 200 square plus j omega 0.4 over 200. So this is my u, and then omega over 200 is my u as well. So this is 1 minus u square plus j 0.4 times u, and 0.4 is 2 zeta. So that's my second order pole. So when I'm drawing the Bode plot for this, how it's going to look like. Now, what frequencies do I have? I have 10, 100, and then I have 200 for omega n. So let's go ahead and create the axis. Let's say 0.1 we start, 1, and 100, 1,000, and 10,000. That should be good enough. Magnitude of dj omega n decibels. 20, 40, 60, negative 20, negative 40, negative 60. All right. Who's going to tell me? I don't want to write the whole thing. Who is going to tell me what will be the Bode plot corresponding to this factor?
Which one?
Constant factor, gain, constant gain. What will be the Bode plot corresponding to this factor? Remember, you have to draw the Bode plot corresponding to each factor: gain, zero, real pole, and the second order pole. So 4 lines are going to be there, and you're going to add them together to get the complete Bode plot.
Does that part become like a constant but an offset?
That's going to be gain, the total gain of the, or what we call modified gain of the plot.
Is it supposed to be that small? I got 0.5. Yeah,
because remember, the numerator is 20,000. So that's 20,000 or 40,000. That's 1/2 anyways. So that's going to be 1 over 200. So that's going to be 0.05, right? So that's going to be a negative value of gain in decibel. So calculate the value.
I had 0.005.
0.005.
20,000 is supposed to be 2,000.
2,000 times 10. So 20,000 divided by 40,000. That's 1/2. And so 1 over 200. So 1 over 2 is 0.5, 1 over 20 is 0.05, and 1 over 200 is 0.005. Yeah. We can increase this just to, hold on, let me increase this so that we can get, or you know what, don't worry about it. Just calculate the decibel for 0.005. It's going to be negative what?
Negative 46.
Negative 46 decibel. Okay. So our constant line is at negative 46 decibel. So let's say this is negative 50 and 46 will be somewhere here. Negative 46. So it's attenuation basically. It's not a gain really. But just for the sake of plotting it, we're going to plot. So that's for my modified value of the gain. Okay, what will be the Bode plot corresponding to my 0? 1 plus j omega over 10. How it's going to look like?
When it reaches 10, it should be at positive dB.
When it reaches,
it should be 0.
It's going to be 0 up to what?
It's going to be 0 up to 1, and then from 1 to 10, 20.
No. This thing is going to be 0 up
to 10.
10. It's going to be 0 up to 10, and then what's going to happen?
Increases 20 decibel.
20 decibel per decade. So at 100, it's going to be 20. So it's going to increase by 20 decibel per decade. Okay, so that's my 0. What about my real pole? What's going to be the Bode plot corresponding to my real pole?
We have a pole 0 up to 100 goes negative 20 dB per decade.
So it's going to go 0 up to
100. Yes, 100.
100, and then it's going to be negative 20 decibel per decade. Okay, so at 1000, I'm going to get negative 20. So negative 20 decibel per decade. And finally, my second order pole. So as we discussed, for the second order pole, if u square is quite smaller than 1, that is, it's quite smaller than 200, omega is quite smaller than 200, then it's going to be 0. And when it's going to become quite larger than 200, then it's going to drop by negative 40 decibel per decade. So asymptotically, I'm going to draw, and then we're going to create the curve. So let's say, let's choose blue. Let's say it's going to be up to 200. So let's say 200 is here. Let's say, assume this is 200. It's going to go up to 200. And then it's going to become 40 at 2000. Let's assume, because I'm just drawing it freehand. At 40 right here. Okay. So the asymptotically is going to, what to draw? Asymptotically is going to, it's going to go along that line eventually. Negative 40 decibel per decade. Okay, now two things we want to do. We want to find out what is the resonant frequency at which you get the peak value. So if we go and calculate resonant frequency, omega r is omega n times the square root of 1 minus 2 zeta square. 1 minus 2 times zeta square. So 191.83, a little smaller than omega n, because zeta value is quite small, 0.2. So omega r and omega n are very close to each other. So again, if you're doing approximation, you don't really have to go calculate omega r. You can still use omega n and show. But that's like 191, which is very close over here somewhere. 191, which will be omega r. 191 omega r.
What was the calculation you just did?
Oh, I calculated the resonant frequency using this.
Oh, okay.
The peak is going to occur. At resonant frequency, peak is going to occur. And the value of peak is going to be 2 zeta square root of 1 minus zeta square reciprocal of that. I need two monitors, so bad. All right, so the peak value is going to be 2 zeta 1 divided by 2 times zeta times square root of 1 minus zeta square. 1 minus zeta square. So the peak value is 2.5516. Yes, right here. Yeah. Oh, 2.5516, and then we're gonna take. Are we taking the decibel of that? I believe we are taking decibel of that to show the peak value, but this is not in decibel. So let's take the decibel. 20 times log 10 of n feet. So 8.1361. That's the peak value in decibel. So that's 10. So 8 will be something right here. Let's see.
And the peak happens at the 191.
191 radian per second, yeah, which is very close to 200. So again, if you're doing approximation, it doesn't really matter. As you increase the value of zeta, then omega r and omega n are going to differ a little bit. As you go smaller value of zeta, they're going to be very close to each other. But still, they will be close to each other. So I'm going to, this is my peak, let's say 8 decibel or something. So it's going to rise a little bit, something like that. And then it's going to come down. And that is going to be my second order curve. Rise and then come down. And then eventually it's going to merge asymptotically with negative 40 decibel per decade. So I'm going to delete this part, this. And finally, I'm going to add everything together. Okay, so I have negative 46 up to 10. So there's nothing else. I'm just going to do negative 46. At that point, I start increasing at 20 decibel per decade. So I'm going to go up a little bit, 20 decibel per decade. And I'm going to get to, what was that? 191. So let's say I'm going to go to 100, about 20 decibel. And then that's going to make it to negative 26 decibel approximately, negative 26 if I go up to 100. And then I further go to 200. So 191, I have, I'm increasing a little bit more per se. Something like that. And then I stop decreasing actually by negative 20. So this is going to cancel each other. So I will only have this left at 100. And it's going to go up a little bit. And then it's going to become constant at negative 26 decibel. Something like that.
Keep
Oh,
going.
no, sorry, this is negative 40 decibel. Sorry, yeah. I forgot that negative 40 decibel. So it's going to go down actually. So it's going to go up. These two cancel each other. And then it's going to start going down with negative 40 decibel per decade. Let me delete that. Clean up. Something like that. So it's gonna be along the same slope as this line, basically, because these two are going to cancel each other. So that's how the complete Bode plot of this is going to look like. Let's draw using Bode function and then see how close we are. Again, this is freehand, so it doesn't really matter. And second order system with freehand, it's not very easy to do. If you have a single pole or double pole even, that's okay. But second order is hard to do with freehand. So the project that I'm giving you, of course, it does not require you to have second order system, but we can incorporate, and then it's going to give you a very good approximation. But we have the Bode function. Let's draw that. Actually, let me see. Bode also give the Bode. It's also give the phase right at the output. Why you have to run it every time? It should just, once you run it, it should keep it. Magnitude, phase, W. Okay, so let's do that so we can calculate magnitude and phase and the frequency over which we have to do. All right, so let's define the system first. So my system is my transfer function, and I have transfer function 2000 as, so my 2000 times 20,000 is my numerator, and what do I have in the numerator? So I'm gonna go ahead and calculate a polynomial using the poly function. Poly, and the roots are -100, roots of 1, 80, 40,000. Is so that it will make a row vector of roots, so that, and then poly. All right, so let's see if it will work. Okay, so the transfer function is 2000 plus s cube plus 180 s square plus 4.8 exponent 4 plus 4 exponent 6. Okay, let's hope that this is correct. So let's say magnitude, phase, frequencies, Bode. Okay, so I have to plot it now. Semi log x w comma mag. All right. Why is showing small? Maybe it did not do it in. Okay, let's go back and just do Bode. So Bode of system. It's better, I guess. So if we compare, so this is phase and this is, of course, your magnitude. So if we compare this against ours, so we are starting at, where is it? Right here, -46. I'm assuming this is -46. And again, this is the exact, this is not approximate. So we are going all the way, as you see, 100, start increasing. And then you have this curve right here, which is going to, let's see what is the peak value that is showing us. Peak value approximately -18.8. It's going to about -18.8, and then start decreasing with -40 decibel per decade. So our curve is correct, of course. It's not exact, it's approximate, but it is what it is basically. This is the exact curve right here, of course. So again, this kind of peak is going to be the result of the second order rule. Just remember that anytime you see this type of peak. All right, I think this pretty much wraps up the discussion of Bode plot, and I know it took a while, 2 classes, but generally Bode plots, it does take time. I don't know why did I put only 1 class, but usually it does take approximately 2 classes. Once again, exact Bode plot, we can always use Bode function, or we can just do 20 log of the transfer function. Even if you're not using Bode function, you can still create exact Bode plot by taking the magnitude of the transfer function and taking the logarithm of that magnitude multiplied by 20. Plot that. That's going to be your exact Bode plot. Bode plot are not exact, by the way; they are approximate, and that approximation, of course, is part of your project as well. And I hope you did understand what you're doing in the project. Again, there's no second order system. There's no J square. There's no complex root in the project. It's only real poles and real zeros. That will make it very easy when you create the conditions that up to this value is going to be 0. After this value is going to be omega over omega c and stuff like that. I had one more thing. If you have the Bode plot, how you can determine the transfer function. We have some time, so let's do one example real quick. Let's see. And again, if you have a question, please go ahead and ask. I talk most of the time. Andre has been, I think today only Andre and perhaps Nicolo, they responded back. Andre has been responding back constantly, but everyone else is quiet. I have no idea if you guys are getting anything that we are discussing, and even if you're there or not, to be very honest. So again, if you have questions, please ask. I cannot see you like I see you in the class, and I can ask question in the class, but here I cannot even see you. That's one bad thing about RTV class. It's convenient for you, it's convenient for me, but I don't know if the learning is as much as in face-to-face classes, to be very honest. Okay, so let's assume that we have T as equals, oh no, we are doing the Bode plot and then doing TS. So let's say we have the Bode plot. And the Bode plot is let's say this is your Bode plot. This is 50 decibel. Let's say this is 0.1. This is 10. This is 100. And let's see. This is, let's assume this is 70. No. Let me make it simple so we can do it instead of, let me just take the 1000 and those frequencies. That will be easier. Let's say, instead of doing calculation of everything, let me write down first frequencies: 100, 1000, 10,000. And let's say it goes 70 decibel. becomes constant. Then it drops down to so let's assume this is our Bode plot. So 10 plus 4. So it starts at 50 decibel up to 10 radian per second. At 100 radian per second, it is 70 decibel. It stays at 70 decibel up to 1000. Then it drops down to 10 decibel at 10,000, and then keep on going. So if you want to write down the transfer function of this thing, the first thing that you have to realize that this is 20 decibel per decade. What is this? Although it doesn't look that much, but what is the slope of this? So it's going to tell me.
Is it a first order or second order?
No, I'm just asking you what will be the slope of this line. Just by looking at the values that you see, what will be the slope of this line? There is no second order equation involved here because you don't see any peak or anything.
Oh, okay.
But what will be the slope of this line?
Negative 60.
40.
Negative 60, because it's going from 70 to 10, a drop of 60 decibel. So that's going to be negative 60 decibel per decade. From 1000 to 10,000, it is dropping from 70 decibel to 10 decibel. So negative 60 decibel per decade. Okay, so if this is your Bode plot, and I ask you, so what will be your transfer function for this? How are you going to write down the transfer function for this? So h of j omega. $50 decibel. Now this will be the modified gain, remember. So in the transfer function, of course, you don't put decibels in the transfer function unless you're expressing it in decibel. So if you know, but what will be the value corresponding to 50 decibel of the modified gain?
300.22.
Right. So you have what, 50 decibel, right? So you have 50 is equal to 20 log 10 of the actual value. Let me write it down so everyone can see it. So this 50 decibel is 20 log to the base 10 of the gain value, whatever is there. So the value of gain is going to be 50 over 20, 10 to the power 50 over 20.
Would you prefer for us to write it like that or the whole number?
What do you mean?
I mean, it's like cleaner if we do 10 over to the power of 50 over 20 instead of just value.
316.23? Is that
I mean,
what 10 over 50 or 20 or 316?
Yeah, I mean, would you prefer us write this 360?
Yeah, that's fine. That's fine because if you put this down, of course, I knew that you did the calculation properly. Because this is the modified, we'll bring it down in the actual value of gain.
Yeah.
All right. Now decide. Okay, so now the curve is changing over here at 10. So what is the factor that is making it change, a 0 or a pole?
That is a 0.
A 0 because it's increasing by 20 decibel per decade. Okay, so what will be that 0? That means 1 plus j omega over what?
10.
10, exactly. So j omega over 10. It became constant at 70 decibel per decade at 100 radian per second. What does that mean?
That means there is a pole with the same 1 plus j omega 10.
No, not at 10.
Not 10, sorry, 100.
100, exactly. So a pole started, a cutoff frequency, a pole with a cutoff frequency started at 100, start going down at negative 20 decibel per decade. So that negative 20 decibel per decade and this positive 20 are going to cancel each other, and it's going to become constant at 70 decibel. Okay, it stays at that until 1000. And then what happened?
And then it's 1 plus j omega over 1000.
There's one thing missing here. Anyone else can tell me what is missing here? Andre has been responding back. Anyone else? There's something that is missing here.
Is there supposed to be a minus sign because it's going down?
Minus sign where?
Between 1 plus j omega over 100 and...
No. There's no minus sign. There's no minus sign. If you go back and look at the transfer functions that we have, we don't put a minus sign over here. We don't put minus sign. Remember why? Because the system is stable. If you put minus sign, that means your pole is going to be on the right-hand side of the S-plane, and the system is going to become unstable. These are stable systems. So the minus sign is not the correct answer. Anyone else? Or Kevin, if you know what is the other thing that is missing. I'm pretty sure Andre knows, but anyone else who can, looking at the plot, looking at the slopes, anybody can tell me what is missing from there.
Is it missing a square, or actually more than a square?
Yeah.
So it has to go down 60 decibel per decade, but the way it's written in the transfer function, it's only 20.
So what power should be there?
It should be 3.
3, exactly right. So that's going to be a cubic power. There are 3 poles that have the cutoff frequency of 1000. Now, so if I create the individual values, individual lines, then that's going to be 50 decibel. There's going to be a pole that is starting at 10. I mean, the 0 that's starting at 10 with 20 decibel per decade, which will increase this line. There's a 0 that is going at negative 20 decibel per decade. The 0 and this pole and this 0 will cancel each other. And that's why at 100, it's become constant at 70 decibel per decade. And then at 1000, since these two are canceling each other anyway, so they're not going to count. Now this is going to start at 1000. And the slope of this is going to be negative 60 decibel per decade, which means that there are 3 poles with cutoff frequency 1000 radian per second. So this will be our values from the graph. Now, when you're writing the transfer function, of course, you're writing in terms of S. So we're going to go back and we're going to clean this up a little bit. H of S is equal to 316. So this is going to be, I'm going to multiply it by 10. So 316.23 over 10. S plus 10, j omega becomes S. And then here, multiply 100. So S plus 100, 1 over 100. And here you have 1 over 1000 cube, S plus 1000. Cube. So now this is the gain, this, and this. So you can calculate that. So that's going to be simple 31.623. So 31.623, and this is going to go in the numerator. So times 100 times 1000, that's going to be huge gain. Times 100 times 1000 to the power 3. So 3.1623 exponent 12. The HS is 3.162 exponent 12 s plus 10 over s plus 100 and s plus 1000 cube. So that's going to be the transfer function of this control systems from this Bode plot. All right, guys, any question about this?